Hello everybody, we're going to code a Hexdump clone today. Hexdump is a tool that allows us to represent any file, any input data, whatever we want, any data, as hexadecimal. So if we just generate a long string of stuff and we pipe that into Hexdump, let's just pipe it into Hexdump, we get a hexadecimal representation of the content of whatever we piped into it. That's nice, right? And if we append -c, we get an even better formatted output that is outputting the input in the right byte order, I think with the most significant bit first. And it outputs the memory location. So this is the starting memory location 0. Then this is address 1, 2, 3, 4, no, 0, 1, 2, 3, 4, etc. And then those addresses are the addresses starting with the one here. So this is a decimal 16. This is a hexadecimal 10. So this is address 16, 17, 18, 19, 20, etc. And then on the right hand side, there's a column that outputs everything that is in the left hand column in plain text data. Now, of course, if we have truly random data or if we have data that contains special characters, then outputting this is not as straightforward because, for example, if we have a string that contains new lines, such as this string right here, the echo, by the way, automatically appends a new line if you don't specify echo-n. Then the last character, this 0a, this is a new line, and this is represented as a dot. So all the special characters that would break the formatting of this output, they are represented as dots. We're going to implement such a thing today in pure C. So let's go. I'm going to call it my Hexdump -c, and then we have to first input or include standard io.h and include standard lib.h, and let's start with a main method. And now we have to somehow read the input memory that we feed in via standard in. We can do that by creating a character variable, and this character variable stores the values of the characters that are coming in from standard in, and we read until we reach the end of file. Obviously, we can't read beyond that. And then we print out the character C. No, we have to specify a format specifier, of course. Let's just print it to the console, and let's go here. By the way, I've already tried recording this, but I just didn't turn my mic on, and now I have to re-record. But we didn't do too much. So this is the file, my Hexdump. I'm going to compile it. The output file is going on. Oh, wait, I have to enable all warnings, even extra warnings, debug flags. The output file is going to be called my Hexdump. And the input file is my Hexdump-c, and it's now compiled. So let's execute my Hexdump. And now, of course, it's not doing anything because we don't pipe any data into it. So let's pipe something, hello, and let's see what it does. Of course, it just prints out hello because we are just printing back the characters as we input them. Now, the magic comes when we specify format X for hexadecimal, and then it's already printing out hexadecimal. How nice is that? However, this is not really properly done, because if we compare that output, let's echo hello into the real Hexdump for comparison, then you can see that the last character is 0a, but here it is just an a. That is because our implementation truncates the 0 because it thinks it's not necessary, but we have to we have to print the 0 because 0A is an ASCII character. It's the new line character. So we cannot just ignore it. We have to specify, I think we have to specify a width like this, or x2. There's some way to specify a width. Maybe like this. Let's try. No, this is the window. Okay. And now it's printing out 48656C, 6C, 6F, and then space A instead of 0A. So how can we make it print out a 0 here? Do I have to write 0? Wait, I have to already look that up online. No. Where's my browser? There it is. Okay. So printf pad with 0 hex. We almost had it. It's percentage, the format specifier, 0 to x. What did I do? Percentage? Didn't I try 0 to x? Yes, I wrote down 0 to x and then just didn't try it. Oh man. Okay, so let's see. And this is now working. So now we are really printing the characters as a full hex representation with the zeros here. That's very good. All right, at the end of all of that, of course, we should have a new line, because otherwise it's just annoying to look at the output. And now the output looks as such. So we get a proper hex representation of whatever we input into our own Hexdump. Now we also have to separate the individual characters with spaces, and now the output looks like this, which is already very good. Now we have to we also have to print the memory address here. We can print the memory address by tracking it. So let's create an integer memory address. Let's call it memory I, or just memory. Maybe I is better because it's an index that's incremented. So I is usually more intuitive for programmers. And while we loop over the characters that are input, we increase the memory address. So we print out the first character. We know the memory address is 0. And then we increment that, and then we print the second character, and then we know the memory address is 1, etc. And for the first memory address, if the memory address is 0, we want to print the memory address to the console. So let's just do that. If the memory address is 0, we can just write a hexadecimal 0 just because it's fun and because memory addresses are usually denoted in hexadecimal, but this could of course be just a 0. But let's do 0x0 just for fun. If the memory address is 0, then we print the memory address. So printf, and we print a hexadecimal representation with x again, and it must be 8 characters wide. Mem I. Okay. Why 8 characters? Well, I think it's because those are 32-bit memory addresses, and therefore we have to use 8 characters. 8 characters are 4 bytes. 4 bytes multiplied by 8 is 32 bits. So this is a 32-bit memory representation. And let's see what our program does if we use it, and it's doing nothing. Why? Oh, of course I have to initialize memory address I have to give this a value, otherwise we don't know the starting value. Let's see what it's doing now. Yeah, okay. And now we get a starting memory address that is 0, but there's no space afterwards, so it looks like it's 00048, but that 48 is actually the capital H here. So let's also add the space here and print it to the console. So now it's already very, very similar to the actual Hexdump. However, when we print a long message, for example, hello, is it me you're looking for? Then we get a long string that doesn't wrap around, but we actually want it to wrap around at this memory location here at 1, 0. So whenever the second digit increments, so every 16th character, we want to wrap around. So first we start with 0, then at 1, 0 we start the next line, then at 2, 0 we start the next line. How do we do wraparounds in programming? We always do modulo. So instead of checking if the memory address is 0 and then if the memory address and then doing, or that would be catastrophic, or memory address is this, or memory address is equal to this, etc., and do that for infinity. Instead, we do just memory address modulo 0x10 is 0. So for every 1/0th, so every 16th memory address, we print this. All right, let's see. And I get a warning, and that's perfect. It's awesome, because that's the reason why I enabled the compiler warnings. So in function main, suggest parenthesis around the comparison in operand of and. Did I put an and? Oh, no, I have to put a modulo. Okay, so we have to be careful here. So now I don't get any warnings anymore, and let's see what happens. And this is the original Hexdump, of course. Let's replace it with my Hexdump. And we still don't get, we get a change. It prints out our first address, this is address 0, but then here it prints out the address 10, and here it prints out address 20. So the printing out of addresses works. However, they are not separated by new lines, and separating by new lines, we could just do it before the printout of the address. Let's have a look at how that looks. And this formats the output just like this. Looks perfectly fine, actually. Now, what I don't really like, although it's perfectly fine, but it's not as neat. It's just 99% instead of 100% perfection. It prints a new line at the beginning of the output, and that is wasted space. So let's remove that new line here. For the first memory address, we don't need a new line beforehand. So let's just print the new lines later. We could do, if the memory address is this, then we print the memory, the memory location, of course, the memory address. Then we print the first character, and no, wait. We have to somehow ensure that after the last entry here, there's a new line. I don't know if that's good. I'm not a fan of this, but let's see if it works. Let's see. Okay. Let's compile and try. And that's exactly the output I wanted to have. Yeah, I'm kind of repeating the if clause here. But it seems to be working well. Okay, let's just continue. We also need the string, the clear text output here. And that's actually the hard part. So how do we do that? Whenever the key issue is that we are piping information into our program, into the process. And the process is reading the characters and then acting on them and then looping over every character individually. So when we are printing out the first character, then we actually need to also print out the first, well, we need to print out the first characters, the first character in hexadecimal, and then we also need to print out that same character in ASCII. This is difficult because we would need to somehow use these weird terminal operators that make the cursor shift back and forth. That's not so nice. So instead, I would propose to, instead of looping over every character and then just doing some printout, I would say we should store the whole line of data in some buffer. And then we print that buffer as hexadecimal, and we print the same buffer again as text. So we can act on it twice. And then we, of course, erase it. So what we have to do is we have to create a buffer. And I'll just do a character pointer and call it string or buffer string. Let's call it string, S string. And allocate space for it, calloc, and calloc ensures that it's initialized with zeros, and that's very important because we're dealing with strings and printouts here, and we definitely don't want random data to be inside that string. Otherwise, we'd get bogus output. So we want to allocate 16 digits of space, and 16 characters of space, size of character. Do I have to do a cast here? I think I have to do a cast here because this is normally returning a void pointer. Now I have the string here. And at the beginning, when we are reading the characters, we enter a string at index memory I modulo 0x10. So starting at index 0 and then ending at, then we never go beyond index 15 because index 16 would be eradicated with this modulo here and reset to 0. So it wraps around to 0 after 15. So we write the characters into this string. And then here they check if we check if the location is the starting location, and we print the memory. Then we print the wait. Wait, we first have to read all the characters into the string, I think. No, we are reading memory locations here. Then we're printing out this. Then we're printing out this. Or, no, we're actually storing already all the characters of the string. And then for the last memory address, which is here, we can print out. Well, here we can, let me just add a comment. Last memory in row reached. Last memory address in row is reached. And then we print the string as a string. Print clear. We print clear the string, the given string, and the length is 0x10. And that can be a new function. Void print clear. I hope it works that way. So we create a new function, character pointer, string, and then we give it a length. And then for every character in the string, we print out something, and we don't print just the entire string. We could do it. Well, let's actually do it and see what the result is. But I already know. Oh, well, I don't know if that even works, because probably we don't have a terminating 0 character at the end of this. Oh, let's just see. Let's just see. So we print as clear the string, and then we print a new line, and then we do something. Okay, now I completely lost what we are about to do. And if this even works, let's see what happens if we compile and it doesn't work because the parameters are unused. That's fine for now because that's intentional. And okay, so we echo hello, is it me you're looking for into my Hexdump, and it seems to be working. We print out the memory location, the hexadecimal contents of the input, and then we output, and we also format that same thing as the clear text string. So that's working. However, what happens? Well, it's only partially working because our printout doesn't contain for special characters here, and it doesn't account for the last line. So now we have to also put our string here. So let me just show you the special character thing. What's a file with special characters? It's, for example, our source file because it contains the new lines. So let's cat our source file, my hexdump.c, into my hexdump. Wow. Inception. Okay. And as you can see, the output is now completely messed up because after every new line in the source, there's also a new line in the output of this program. So this is not working well. So we have to guard our print clear statement. So let's do that first. We have to modify it. We have to loop over the individual characters of that string ourselves. And then we print something. We print the character as at index I that we're just right now looping over. And this is right now the exact same thing as printing the entire string. And now we just ensure that there are no special characters. How do we do that? We can just go and check the ASCII specification in the man pages. And as you can see, ASCII characters, here they are represented as hex. And this is the clear text representation. They have all kinds of special characters. For example, substitute, escape, file separator, group separator, who God knows what all of those are for. The most well-known is probably the new line separator somewhere. Yeah, there it is, 0A, and this is a new line. And we want to ignore all of those special characters here. The space, printing of the space is fine. And this has the hexadecimal value 20. So we can start and we can check if the input into our hexdump has values below 20, then we just print a dot as a replacement. And that's exactly what the official or the original hexdump also does. And then we can print all those characters going up to, well, that's just the alphabet here, going up to, maybe the delete thing should be ignored as well. So going up to 7E. So from 20 to 7E, we can ignore characters. And that's, by the way, one thing that we have already done in one of the last episodes, where we coded a string extractor ourselves. There we also had to determine what stuff inside a binary file is a string and what is not. So we extract only the clear text stuff. So if you're interested in all of that string stuff, then also have a look at that string extractor video. It's very, very interesting and fun. Okay, let's check if the current character si is smaller than 0x to 0, or no, smaller than or equal to 0x to 0. So we allow the space character. Then we ignore. No, then we print a dot. Or s at index I is bigger than or equal to 0x7e. Then we print Then we print not the character, but we print a simple dot. Just replacing the special character in the output. And if that's not the case, so in the else case, we do a print of the actual character. So I can also put a comment here, print the actual character. And this is replace special character with dot. Okay, let's see. Let's compile all of that. Compile, and let's test it with our simple input. Hello, is it me you're looking for, which doesn't contain any special characters. Well, actually it does. It contains the 0a. But it's located at the end of this, so we don't really know what's going on here because we don't handle it yet. But a better test would be, of course, to test it with the source file, which contains plenty of special characters. Let's try. And as you can see, now we have a this is awesome. Now we have a well-formatted output depicting all the memory locations in the file, the hexadecimal contents, and the actual code and all the special characters, the new lines and whatever else there is replaced with a dot. Oh, the spaces are also replaced with a dot, but I think it looks good. Yeah, because here we replace even if the character is a space. Should we do that? I think we should do it because that just ensures that all of that output is very neat. If we replace that with spaces, or let's just try to include the spaces. And also I wanted to include the tilde character. Let's try again. Let's see what looks better. This is just an opinion. Yeah, this is fine. Now it's representing spaces as spaces, but I think the other one looks better. So let's also replace spaces with dots, and let's also replace the tilde with, oh no, the tilde can stay. Okay, and we have this output. Very nice. Now actually you might think we are already done, but we are not. We are not done because let's pipe hello, is it me you're looking for, and it's outputting this and it's ignoring the OR part at the end. So it's truncating the output. It's outputting all the hexadecimal data, of course, but we haven't converted the last line that contains much empty data or no data here as a string. We don't represent that yet, or we don't cover that case yet. How do we do it? How do we do it? We have to, at the end, when we have read the file, then we know that the last line was not complete and this if statement here was not executed. Because this is only executed if, well, the end of the row is reached. As you can see right now, the end of the row is reached. And this is executed. End of the row is reached. This is executed. Here, the end of the row is not reached. And this is not executed. The string output is not executed. That means we have to do it down here. So we have to now how do we do it? We have to first of all, fill up all of that non-data with spaces. How do we do it? There's a way to do it in printf. There's a way to do it in printf. Let me just look it up. Printf variable length padding. Let's see if I can find it. Yeah, we can use the asterisk in our format string. It gets a number from the arguments. As you can see here, the number is 3, and then it prints 005. It prints a variable width here. So you can only pad with spaces or zeros. Okay. So let's go ahead and do that. So we print f asterisk. Was it done like that? Then let's say 5. Then a space. And then we print, let's print f something like test at the end of this, just so we can see how many spaces there are. Let's compile that and go. Okay, so as you can see, there are a couple of spaces, and then there's our test output. I just entered the test output here to make sure, to see visually where or how much padding there was generated. If we increment that number, for example, to 30, then the test is moved to the right. So how many times do we have to move the test to the right so it's properly aligned with this text here? We have to move it, well, it depends on the length of the line. The length of the entire line is 16 multiplied by 3. 16 because we have 16 characters in a line. I mean 16 data points in a line that we translate, that are stored here. So this is one character, this is one character, this is one character. And every character in the memory is represented as 3 characters here. It's a hexadecimal number, which consists of 2 characters in the representation followed by a space. So 16 multiplied by 3. That's the entire length of that string. So we can do 16 multiplied by 3, and then minus this, the length of the last line that was printed, and then we know how much padding we need to enter here. So the length of the last line that was printed can be actually determined via memory I, because memory I is still set to 0 here, 1 here, 2 here, 3 here. And then we just exit this while loop, and memory I is of course incremented properly all the time. So we can just use minus memory I multiplied by 3 also, because every represented memory data point here takes up 3 characters of space. And that should be it, right? And we can even put all of that in parentheses. So 16 minus memory I. Let's see. And now the test is moved all the way up here. So this is definitely wrong. Where did I go wrong? 3 multiplied by 0x10. That's 16 characters. Minus memory I. What's wrong here? Actually, I think it should work now. But it doesn't. 0x10 minus memory I. What is the value of memory I here? Is it maybe wrong? I'm not sure. What if I just enter memory I minus 1 just for experimentation, and let's see what happens here. Still not correctly aligned. Why does this not work? 3 multiplied with 0x. What if I just write a 16 here? That shouldn't make a difference, right? Yeah, right. string Am I stupid? We have to calculate how long is this line. Then we subtract this. And then we know how many characters are left over. If I'm not completely stupid. But apparently I am. Because it's completely logical to me. But apparently it's not working. So I must be wrong. The computer is never wrong. Or whatever I write or the instructions I give the computer are wrong. That's of course also possible. 3 multiplied with what if I just do 2? Am I wrong about my assumption that every... No. Minus mem I. Of course I have to modulo the memory with 16 because the memory address, the mem I, is of course an absolute number starting from 0 and then it's incremented up to the last address. But of course, I want just the address relative to this starting address here of the respective line. So I have to modulo with this. I think now it should be working. Now I'm fairly certain. And now it's properly aligned. As you can see, the test is located right here. And now instead of test, we can just print out, print clear. We print clear the, what do we print clear? We print clear the string s, which is now, which should contain those characters here, and we print clear s with the length of mem I modulo 0x10, and this should work. Okay. And it's working. Yes. Okay. Now, what's missing is we are still missing the brackets. Let's compare the output with the official Hexdump. Hexdump-c. As you can see, all of this is put in brackets. That's simple. Is that even called bracket or a pipe or a straight line? What is it called? Block? I don't know. So we print here printf the straight line, and then we print f at the end of this. Same thing again. Let's try, compile, and pipe it into our Hexdump. And as you can see, this is looking exactly the same, except we are printing the spaces as dots because I found this better. But okay, maybe we have to align with the official Hexdump. But I like this somehow. I just like this. Okay. And now the last thing that is remaining is printing out the end address on a new line. And this should be fairly straightforward. So after the new line, after the printing here, print clear, we need to printf another new line followed by the end address. And the end address is the hexadecimal number 08 padded with zeros to a length of 8, hexadecimal number. And the value is mem I, because it's, of course, still correctly incremented, as you know. Okay. Let's see. And there we go. It's working. This, guys, is our Hexdump. And let's try it with an ultimate test. Let's pipe let's pipe the source code of my Hexdump into my Hexdump. So let's do cat my Hexdump into my Hexdump. Is this full of special characters or what the hell is going on here? Ah, no, I've compiled the I've piped the compiled binary into my own Hexdump. But this is actually also quite interesting to look at, because now we can see what's the compiled content. We see there are some special characters, and then we see some headers, linked libraries, the opcodes, and all of that stuff. So it could be used for static analysis of binaries. But let's pipe the source code, and this is it. All done via our own custom Hexdump implementation, which works perfectly fine. I'm actually surprised it works that well. So we are printing memory addresses here, the hexadecimal contents of the file, and the same content as a string representation. And now to make it absolutely identical, okay, I give up. We have to also display spaces properly. So this is now our final implementation of a working Hexdump. Let's compile it and see the output. And let's go. This is now a working Hexdump. We can see the hexadecimal data in the memory, in the respective memory locations. And we can see all of that translated to text here in the right-hand column. And we can see the end address, the final address of the file down here. That, guys, is our custom own implementation of Hexdump. If you enjoyed this, leave a like, stick around, subscribe. And if you're interested in supporting this channel, then consider becoming a Patreon, consider buying the bash or the theme and all of that stuff, my terminal setup on Gumroad. I have put a link in the description if you like how my terminal looks and how everything that I do here looks like. Then you can set all of that up very simply on your own machine. And actually this machine I have just set up yesterday evening, and it looks exactly the same as the other machine I was working on all the time on the other videos. So you can really replicate exactly that look on your machine if you're interested. Anyways, stick around, subscribe, leave a like, all of that stuff. Put a nice comment, and your feedback is always very well appreciated. Bye.